Okay. Okay, so the type of problem we did not get to yesterday was the type where it gives you information and asks you to write the equation. So in this particular question, we can use the following information to write a trig equation that will model the situation. In a certain coastal location, we know the depth of the water in the sound at high tide is 14 meters. The depth of the water in the sound at low tide is 5 meters. The last high tide occurred at midnight, which we're going to call t equals 0. And the next high tide occurred at 11:50 a.m. That's t equals 11.83 repeating, because you've got to do 50 divided by 60 to get that decimal there. It's got to be all in hours. 1150 is not 11.5, right? 11.5 would be 1130. Mm-hmm. Five had a chart, didn't it? You might have had to do that for your time, but I think it was a little different. We can look at it. Because you found your equation by typing it into Desmos on that one. Okay. I think that it's not because you need to know how to do this stuff. I think it's because you maybe had a question about what it was asking there. So one thing you could try, and I'm going to show you that it doesn't really work, is you do know low tide and you know high tide and you know when they occurred, right? So you may think to yourself, well, maybe I should just come up with, I should just put this into Desmos, right? So if I try that, it would be a great idea. And it would be easier than thinking through it, but here's the problem. If you put in your table, and so high tide was at 0, and the water level was 14. Low tide was at 1150, which is 11.83 repeating, which was, I'm sorry, at 11.83 repeating, actually, it was high tide again. Right? So that was 14. So that gives us that point. And then if we try to do y1 squiggle in a sine bx1 plus c plus d, it just gives us a straight line, which is not a trig function, which is not what we're looking at. And I think if you go with low tide being in between, which would be at 5, if you go with that being exactly halfway between, so 11.83 repeating divided by 2, that's 5.916 repeating. So like that makes sense. We've got these points right here, but does that look like a good graph for what we're looking at? It does not, because this should be high tide, right? We should have maximum points right here at these points instead of that. This graph is done like that's the midline, and it has high tide way up here at like 23. So you have to have more data points than this for it to do a good job on finding your sine regression for this, because we should see, I'm going to leave this up because I want to graph it once we do find our equation and see if it looks right. But the sine regression is not going to work well with just 3 points. It's going to give you something crazy. So you need more points to be able to do sine regression. So we're going to have to reason through this one. All right, so first of all, high tide was at midnight. Which function would be easier, which we're calling t equals 0, which function would be easier to deal with if high tide is at midnight? Cosine, right? Because cosine has a y-intercept at a maximum, which means if high tide is at midnight, we don't have to shift this left or right. Okay? So you could do it with sine, but you're going to have to shift, which makes it more difficult. So let's choose cosine for this. So we're going to have y equals a cosine b x. If I use cosine, do I need a plus c? Do I have to shift it left or right? I'm going to not put a c there. I'm going to put plus c right there on the end. Because since I'm using cosine and I know that I've got high tide, which is our maximum at midnight, I don't have to shift this left or right. So I left off the c here. So let's think about like what we're graphing here. High tide is right here at 14. Low tide is at 5. Okay, where's my midline going to be? How do I find that? Okay, 9.5. Right here. Is that halfway between 5 and 14? 5 plus 4.5 would give us 9.5. 9.5 plus 4.5 would give you 14. There are lots of ways you could think about that, but you could just average these numbers. 14 plus 5 divided by 2, right? Which is 19 divided by 2, which is 9.5. Right? If you need to know the number halfway between something, you can just average them. Right? So that is my midline, 9.5. So that's the D right here on the end. So I've got cosine bx plus 9.5. Okay, and now that I know the midline, I can find the amplitude, right? Just take 14 minus our 9.5, which is going to be 4.5. Or Caleb, you actually kind of found the amplitude first, right? As you were doing that out loud. He said 14 minus 5 is 9. So highest to lowest is 9. You got to take half of it because amplitude is just from the midline to the highest point. So we should have a 4.5 here. Is everybody with me so far? Okay, any questions so far? All right, so we don't have to shift this. We just need to know what number needs to go here for B for the period. What is the period of this graph? 11.83 repeating, because high tide was at midnight. It was back to high tide at 11:50 a.m., right? That's 11.83 repeating hours. So that is how long it took it to start repeating, because then after that high tide, it's going low, then high again, right? It's going to start to repeat. So, so to find our period, we do 2 pi divided by b, and we know in this case that should equal 11.83 repeating. So you can put this over 1, cross multiply, think about however you want. You got 11.83 repeating times b equals 2 pi. And then so if you divide by 11.83 repeating, here, and let's see, what's my calculator? 2 pi divided by 11.83 repeating is going to be 0.53097 . I think on the ones I'll probably round to 3 decimal places, but the more decimal places you keep, the more accurate it will be. Something like this would probably be multiple choice, so you would be able to see where it's been rounded to. So that's our B. So our equation should be y equals 4.5 cosine of 0.53097 x plus 9.5. And that should be our answer. So let's go back to Desmos and see if that fits our points here. So we got y equals 4.5 cosine of 0.53097x plus 9.5, and that fits really nicely, right? So you can see how this one works. The other one went through the points fine, but it didn't have the high tide being correct. The high tide should have been right there at 14, so this one looks good here. So this is a lot like that worksheet that you had with the graphs and the word problems on the back, where you had to write the equation, but it's in a specific situation. So you have to decide what the amplitude is, what the midline is, what the period is, according to tides, not just given to you that the amplitude is this and the midline is this. But it's very similar to those problems and how you actually work them out once you figure out what those are. The reason that I used cosine is because high tide was at midnight, which was t equals 0. So high tide is going to be your maximum point. And cosine starts at a maximum point. It has a y-intercept at the maximum point. So if I use cosine on this, I don't have to shift it left or right. You could also use sine, and you could get an answer that'll work. But to do that, you would have to take, because sine is usually at the midline at your y-intercept, you'd have to shift it to the left or right to get it to match up. So it's just a little easier to use cosine here. Okay, so 2 and 3 are similar to this on the worksheet that you guys had last night. So after you finish your quiz, you are going to work on that, those two problems for me. So I'm going to go ahead and get you guys started on your quiz, and then I'm going to come around to check your homework from last night while you're working on that quiz. So put away everything. No calculators on this. You may have a sheet of paper if you would like. Yes. We do not have time today. But I can answer a quick question on it, yeah. But we need to go ahead and get started. What questions do you guys have from it? Okay. So here's where I think it is a lot easier to use Desmos than the calculator, because if you are using Desmos, you put all this in, you get this regression, it's going to give you the graph. Once you graph it, if you click on that line, it'll have gray dots at the maximum minimum points. So all I did to get these numbers right here was just on Desmos, I would go to like that first low tide, and then that's the x coordinate there, and then the y coordinate would be then the next x coordinate for your maximum. That's these numbers right here. And so what is a little tricky about this is that you need to change it to a date. So first high tide is April 9th, and it occurs here. Use your model to predict the dates and times of the next 3 high tides. So basically, you're just like taking that time and adding it. The big thing that you need to know here, so like this would be 12, obviously is 12 o'clock, and that 0.81, to change it to minutes, you're just going to take 0.811 and multiply it by 60. So take your decimal part, multiply it by 60, that'll change it to minutes. So, and I think I just rounded to the nearest minute there because it wasn't exactly 49. And so, yeah. And then your next one is 19. So now this time 19 is bigger than 12. So you had to subtract 12 from it for your hours, and it was 7 p.m. instead of being 19, because unless you're doing military time, we don't go up that high. So that's where we got the hours. Then just take 0.112 and multiply it by 60, and that's where I got the 7 minutes from that. So this is something that's good to be able to do. Probably not something I'm going to ask you to do on the quiz or test, being able to convert it to that date there.
How did you find the date on problem 4?
So first, maximum. So the maximum that you look at whenever you're looking at it on Desmos, it's going to be at 1. So that maximum being at t equals 1. For this, it tells you t is measured in years since January 1st, 1970. So if t equals 1, that is 1 year after January 1st, 1970. So that would be January 1st, 1971. And then when you do the minimum, it's going to happen at like 3.5. So you're going to add 3 years to this, and since it's 0.5, I did July 1st. If you did like the last day of June, that would be okay, but right there, that break between June and July is the middle of the year. So, you know, again, it's either going to be multiple choice, where I'm not going to give you July 1st and June 30th as two answer choices there, or, you know, it'll probably be multiple choice or something for that. It won't be something where you got to type in the date. Okay, other questions?
So for part F, you just do like 2022 minus 1970?
Yes. And actually, that answer's probably wrong. Because I did not go back. If you did that, I'm not sure when I last updated this answer key. Yeah, it probably is wrong, because I know I did not go update this for 2022. I always like these questions, but it also means your answer key's wrong every year unless you update them. So I need to go through and like put the next, if it is 2023, 24, 25, so that I'll have the answers for the next several years in my answer key. Yeah, that one's probably wrong. Yeah, but you would just do 2022, subtract 1970 from it, and plug that number in. I won't give you one like that on a quiz or test because of the same reason. It's going to be wrong. Okay, other questions? All right, so we have got one quick section that we are going to go over here today, and it is on graphing other trig functions, which is our tangent, cotangent, secant, and cosecant. Okay, we're not going to do a great deal with these because their graphs are generally not nearly as useful as sine and cosine. Sine and cosine are very useful for lots of different applications. Tangent, cotangent, secant, and cosecant are not nearly as useful. You're not going to find places where you use them much in the real world. It is important for us to kind of look at their graphs and see what they look like, but it is not going to be a major thing that is tested. So you'll see maybe a couple questions about these that won't be terribly difficult. I do want you to be able to recognize if you're looking at tangent, cotangent, secant, or cosecant. And I do want you to be able to answer a few basic questions about them, like what the period would be or something like that for those. Okay. So you will not need your computers for this, so you can go ahead and shut your computers for me here. So let's zoom a little bit. Okay, so here's what the graph of tangent looks like. Okay, tangent is going to have vertical asymptotes at negative pi over 2, pi over 2, 3 pi over 2, and so on, right? If you think about what tangent is equal to, tangent of x, what was that identity that we used for that? What was tangent equal to? We had to do it with the unit. Sine x over cosine x. So, tangent has a vertical asymptote when cosine of x equals 0, because that's given it a 0 in the denominator, which means it's going to be undefined, right? So that is a really good way to help you remember where those vertical asymptotes are. Because you should hopefully, at least if you've got a unit circle to look at, be able to tell me where cosine is 0, right? So it's at pi over 2, 3 pi over 2, and then you can keep going around 5 pi over 2, 7 pi over 2, and so on. What is the period of this graph? It is just pi, right? Because if you look right here, our y-intercept is right here. If we trace this, and then we go down here and pick up, it starts to repeat the pattern right here at pi. Okay, so this is the big difference right here for tangent. That's the biggest thing you need to remember about tangent, is that the period for tangent is only pi. For sine and cosine, it is going to be 2 pi. We'll also find that cosecant and secant is also going to be 2 pi. But for tangent and cotangent, your period is pi. That's really important to remember. For our x-intercepts, we can see here for our x-intercepts, we got negative pi, 0, pi. The next one, you can barely see it over there, would be 2 pi. So negative pi, 0, pi, 2 pi, dot, 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 so on. Any increment of pi, you're going to have an x-intercept there. The y-intercept for this is at 0, 0. And we said the asymptotes are anywhere that cosine equals 0, which was at pi over 2, 3 pi over 2. It'd continue on 5 pi over 2, dot, 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 7 pi over 2, 9 pi over 2, and so on. Okay, again, big thing to remember there, period is pi for that. If we look at cotangent, it looks almost the same, but our squiggles, instead of going up, they're going down, right? And our vertical asymptotes are in different spots this time, right? So our vertical asymptotes are no longer where cosine equals 0, because cotangent of x is cosine of x over sine of x. So our vertical asymptotes are going to be where sine of x equals 0. And you can see it on this graph, but we know from the unit circle as well, asymptotes are going to happen at any increment of pi, right? 0, pi, 2 pi, 3 pi, 0, pi, 2 pi, 3 pi. If you go the other way, negative pi, so on. Those are the places where sine equals 0. period for cotangent is also pi. Our x-intercepts are going to be at pi over 2, 3 pi over 2, and so on. You'll notice this is kind of like some of the pieces just switch here. And cotangent does not have a y-intercept. It's not graphed as it is. Okay, questions here? All right. Secant. Secant's a weird looking graph. You have these vertical asymptotes here. And you got sort of these U-shaped, right? So, secant of theta equals 1 over what? Cosine of theta. All right, so watch this. This helps me understand secant a lot. Okay? Let's graph cosine on this graph. So I'm going to, in green, cosine of theta is going to be graphed in green. Cosine begins at a maximum point, right, which would be a maximum of 1. Then midline, minimum, midline, maximum. So here's our graph of cosine. See how it just kind of like fits right in there between? So all of the transformations to secant, if you think about changing your cosine graph, it basically does that same thing to secant there. So if we wanted to make these views like further apart, right, we could change the amplitude of cosine and it would make it taller and it would like spread out the graph there. You could change the period the same way we change the period for sine, all of those things. Since secant is just based on cosine, the period is also 2 pi. You're going to have a y-intercept at 0, 1. Your asymptotes are going to be at pi over 2, 3 pi over 2, 5 pi over 2. And that is when vertical asymptotes when cosine of theta equals 0. Think about on this graph right here. There's where cosine equals 0. You have a asymptote, right? Right here, cosine equals 0, asymptote. Cosine equals 0 here, asymptote. And we're not worried about those maximum minimums. I'm not going to ask you. Okay, questions? And cosecant looks very similar. It's just kind of slid over, much like sine and cosine look just the same, and they're just kind of slid over, right? So, again, remember that cosecant of theta is 1 over sine theta. So if we think of graphing sine right here, sine has a y-intercept at the midline. So we do maximum, midline, minimum, midline. So if we graph this, here, see how it also kind of just like fits right there between the two graphs. And because this is solely based on sine, the period for it is also 2 pi. So basically everything the original period is going to be 2 pi except for tangent and cotangent. You do not have a y-intercept. You will have vertical asymptotes at negative pi, 0, pi, 2 pi, and so on. And if we put a note right here, we'll have vertical asymptotes when sine of theta or x, whatever you want to use there, equals 0, because your denominator would be 0, which is undefined. And we won't worry about maximum and minimums. So I want you to be able to recognize these general graphs here. And then there's a few types of problems that we're going to look at. So one thing I'm going to ask you for is the period of each function. So to find the period for tangent and cotangent, instead of doing 2 pi over b, you're going to do pi over b. Okay? For sine, cosine, cosecant, and secant, you're going to do the same thing we've done for sine and cosine, 2 pi over b. So for the sake of time, I'm not going to do every single one of these, but whenever I'm dealing with tangent or cotangent, I need to do pi over b, not 2 pi over b. So for that first problem, the period of this function, I don't have a number in front of my x, so it would just be pi, right? Because it'd be pi over 1, which is pi. Okay? But if I'm doing something like cosecant, just treat it like it's sine and cosine, right? So for your period here, you would do 2 pi divided by the b value, which is the number in front of your x. So that'd be the 2, which would just give you a period of pi.
So you said that your period can't change to be that if it has 1 in front of it, you can just assume that it's going to be pi.
For tangent and cotangent, yes. Yep. Much like if we had a sine graph that was just like sine of x plus 2, the period for that would be 2 pi. It would not change.
And for the other equations related to like phase shift, you said the period changed, so it was just only what the phase shift by.
Right. Okay. 4. Let me skip down here to 4. X over 5, how can I think about that instead? 1/5 times x. So our b value here is 1/5. Since that's cotangent, though, we would do pi divided by 1/5, not 2 pi divided by 1/5. So we got pi times 5 over 1, which would be 5 pi for our period. All right, you do the same thing because pi is just a number, right? So you take, it's tangent, so we're going to do pi instead of 2 pi, divided by b. The b value is pi here. What is pi divided by pi? 1. So your period would be 1 there. That one's going to be 4 pi if you just want to advance with me. But we need to move. All right. Okay. So let's look at this equation, or this one. It says which could be the graph below. And you really don't have to worry about the midline because all the midlines are the same here. We see that it's at 2. Might help us to draw that in. right there. And let's think about the period of this graph. If I look at the y-intercept and I trace until I get back to start this to repeat, what is that period for that graph? It's pi. So I don't have any numbers in front of my x, which I didn't anyway, right? Okay, so tangent is going to be, if we look back at that graph, tangent here, it intersects the midline right there at our y-intercept. And it has, so like tangent normally would hit the midline right there, right? And this graph looks like tangent because our graphs are doing the increase, right? So, and because they're, now if you reflect it, it does look like it's negative, but these are not reflected, so I'm going to take those out. So, this is not correct. It needs to be shifted over, and if you shift it to the right, pi over 4, it should line up. So you would have C there. I was just thinking about what tangent normally looks like. And tangent, if we go back over here, it crosses right there at 0, 0, right at the midline. So for this one, it should hit right there at the midline. If you think about what tangent of 0 is, it's sine over cosine, which would be 0 over 1, which is 0. So that can kind of help you remember that's where it starts. So the green line is what tangent would be if we just shifted it up to, but we're also going to have to shift it over. And really, you don't even have to worry about how much to. I will not give you like super difficult ones for tangents, cosecant. You pretty much just have to know that's not the normal tangent. It's been shifted a little bit. Oh, there's only one option that's been shifted. I won't give you ones where all of the options have been shifted equally there. All right. Okay, secant of 3, 2x plus 1. All right, so what is our midline? 1. So I'm going to draw in a midline at 1 on all of these and see if that looks right. Does that eliminate any of these? D's out because that does not look like the midline for that one. So that eliminates D. All right, then secant doesn't have amplitude necessarily, but you can kind of think about graphing the secant is 1 over cosine, right? So the amplitude here would be 3, so that distance that these points are from your midline should be 3. So that takes out C, right? Okay? And then this 2 right here is going to give us a period change, right? So we'll have 2 pi over pi, 2 pi over 2, which should give us a period of pi. So if we look at our graph right here, if I trace until it starts to repeat, it goes all the way to over here, which is 2 pi. This one, if I trace until it starts to repeat, it would start to repeat right here at pi. So B should be our answer. Okay. All right, let's do one tangent function right in the equation. Cotangent is no different than tangent except for you use COT instead of TAN. All right, a tangent function that has a period of 4 pi and has been shifted down 5. Okay, I'm probably not going to give you, I will not give you amplitude for tangent because it doesn't really have amplitude. So I'm going to have y equals tangent of BX. Do I need a plus C? No, it's not going to be shifted left or right. The down 5, what's that going to be? Minus 5 over here on the end. So, much like you would do with the sine function, you are going to do, instead of doing 2 pi over b equals the period, we just do pi over b equals the period, which they tell us is going to be 4 pi. Right? So it's the same thing we're doing for sine. The only difference is we're using pi instead of 2 pi. It's really it's the main difference in what we're doing here. The graphs look crazy, but that's the main thing you need to know. And then, so if we cross multiply, we get 4 pi times b equals pi. And we can divide both sides by 4 pi. It will cancel the pi's right there. And b will equal 1/4. So your equation would be y equals tangent of 1/4 x minus 5. Or they might write it as x over 4. There. Phase shifts, you do them exactly like you do them for sine and cosine. They're exactly the same. So if you have a phase shift, that's what you're going to do. So the assignment that goes with this tonight is going to be it's on Desmos Classroom. There's a link on Canvas to it. It's going to be a matching activity. Okay. If you get desperate, you can, I don't want you to try to think about it without using Desmos, but you can always graph it in Desmos to kind of help you if you're getting stuck for those.